Hi everyone, I'm going to talk about our paper exploring and interacting with the set of good sparse generalized item models. In machine learning, we usually follow a standard paradigm where a training set is fed into a machine learning algorithm which produces a predictive model. The model could be linear model, random forest, neural network, any kind of model. Now we use this paradigm for almost all machine learning applications, but there is a problem with it. For high-stakes decision-making problems, we would prefer to use inherently interpretable models so experts can understand them and critique them. But such standard paradigm only produces one model at a time, regardless of the existence of many equally good models. It only allows passive comments and doesn't support the interaction between human and algorithm. We really need a new paradigm, and we designed one. The idea is, instead of finding and storing a single optimal model, we find and store all good models. Then users can find a model that obeys their constraints without worrying about the model performance. And we call this set the Rashomon set. Usually we construct the Rashomon set for a specific model class by finding all models in this class with low objective value. In this paper, we construct the Rashomon set for sparse generalized additive models. Generalized additive model, or GAM, takes this form. It's the sum of shape functions. G is a link function. We use the logistic function for classification. The row 0 is the intercept. Fjxj is a shape function. It operates only on feature j. In our case, we divide continuous feature into bins and get weight for each bin. Therefore, the shape function is a step function like this. The entire model is interpretable since it can be visualized via 2D plots. When a new point comes in, we can find which bin the point belongs to in each shape function and sum the weights to get the score for prediction. In this paper, we find the Rashomon set of GAMs. We find all GAMs whose objective value is less than or equal to theta. The objective function is the sum of log loss, L2 penalty on weights, and L0 penalty on the number of steps. This problem is hard. Finding one sparse optimal model is already hard, but we need to find all. Since we have a continuous space, we cannot enumerate all models, but we can carefully approximate the GAM Rashomon set. When support set is fixed, which means L0 term is fixed, then the objective function is convex, and the Rashomon set is a convex set. We can approximate the Rashomon set by an ellipsoid. The key here is we need to find this ellipsoid carefully. The ellipsoid should be maximized in volume to cover diverse good models, while guarantee most models inside the ellipsoid are actually in the true Rashomon set. The goal is encoded into an optimization problem. The first term represents the inverse of the volume. Minimizing it is maximizing the volume. In the second term, we uniformly sample models from ellipsoid and penalize strongly when the sampled model is outside the Rashomon set. And we solve this problem by gradient descent. For different support sets, we can always apply the method I talked before to approximate the Rashomon sets. But it's time-consuming, and we use a more efficient blocking method. We can first approximate the Rashomon set for a large support set by an ellipsoid, and then merge bins to get different support sets by forcing their weights to be the same. Geometrically, it's placing a hyperplane on the ellipsoid, and their intersection is the approximated Rashomon set for the smaller support set. This intersection is also an ellipsoid and can be obtained analytically. In the paper, we also discussed several applications for the GAM Rashomon set. First of all, constraint handling. We can now easily find the model that obeys different constraints. For example, we can find a model with monotonic constraints. Sometimes users may prefer a shape function that monotonically decreases as it aligns better with their domain knowledge. This can be obtained by solving a quadratic programming problem with linear constraints. Linear constraints ensures the previous step is higher than the next one. For example, the original shape function for blood pressure in the diabetes dataset has a jump around 60. After solving the QP problem, we can find the desired shape function in yellow. And this problem is solved within 0.04 seconds. We can also easily find models closest to users' requests. Sometimes users may prefer a model but it's outside the Rashomon set. We can easily find one within the Rashomon set that is closest to users' request. This is equivalent to solve a QP problem with quadratic constraint. Suppose given a shape function like this, users prefer the shape function in red, and it's not in the Rashomon set. By solving QP problem, we can find the new shape function colored in green. The GAM Rashomon set also supports model-free analysis. For example, it can be used to study variable importance, which goes beyond using a single model, and study the sudden changes in the shape functions by checking many different models. There are more details and application examples in the paper, and thank you for watching.